All right. And yeah, so the projects are done individually, but what I say is that you're allowed to work with other people. So in other words, you need to state who you worked with. All right, that's the way I always do that. So if you worked with like 3 other people, you need to state who those people are. But you know, in other words, I expect you guys to be collaborating on it. I don't expect you to do it in a vacuum. All right. And I would honestly, you know, expect that for the project, you guys will be using the study rooms, you know, probably on a regular basis to try to, you know, help each other out on stuff. Totally fine with me if you're doing that. Doing it by yourself is not going to be a good idea for anybody, I don't think, unless you really want to. Okay. All right. So today, what I want to do is the last part of differential equations that I wanted to talk about, which is numerical solutions. All right, to these. And that's going to be a big part of the homework. So in other words, how would I take this guy here and not do the whole thing where I guess a particular solution and I get the characteristic equation, not that whole thing. But what I want to do is I actually want to say, how do I do it numerically, right? And so last time I started talking about this and I said, all right, I need, you know, there's a lot of places where this would be useful. Right. So I said, you know, one of them is simulators. The other one would be if I got into some digital control or some kind of signal processing, some sort of embedded system problem. Okay. So, you know, if I looked at a simulator, right. So for when I talk about a simulator, what I mean is basically something like multi-sim. A lot of you guys probably use multi-sim to do stuff with your homework or whatever, right? Multi-sim is a simulator. So behind the scenes, that guy is solving differential equations. All right, it's doing it numerically in the way that we're going to do it. It's not guessing solutions or whatever. It's solving time step by time step by time step. So we gotta talk about what that means. Okay. This other thing here, a digital control and signal processing. I gave this example last time, but I wanted to kind of talk about this guy again. So if let's say I had an audio file. So this was the audio file that I played last time. In other words, when I say it's an audio file, this is a WAV file. All right, a WAV file. So I took a WAV file like you'd have on your computer. All right, all that is basically a digitized version of some audio signal that's been recorded. So it's a voltage. It's a voltage that's been put through an analog to digital converter and turned into a file. All right. What I had last time was I played that and it sounded nasty, right? So the example that I played was this guy. So you see, and you're going to have an audio file like this in the project, right? So I got audio read here is the command I'm using. So I do this audio read and I play the sound. And it sounded like junk. Now, something that I mentioned, I said, any audio signal. So I've talked about this from the beginning. Sine waves, we've talked about sine omega t, cosine omega t all the time. Why do we talk about it? Because pretty much anything in the real world that we process is a cosine or a sine. Okay. So if I looked at this wave file, what's in this wave file is a bunch of different sines and cosines added together. So one tool that we're going to talk about later in the semester, some of you guys may have heard this before, an FFT, a fast Fourier transform. It's basically a tool that's used in signal processing to look at that signal there and tell me what frequencies I have information. Right, so I took an FFT of that waveform, and what I can see is all the noise that I was hearing was this guy right here. What this tells me is what frequencies there's information. So the magnitude basically says, hey, there's a lot of information at this particular frequency. This stuff out here, this is the actual audio, and this here is noise. So looking at that in the frequency world, you can kind of start to think to yourself, well, what do I want to do? If I just want the audio, I want to find some way to just extract this stuff and get rid of that, right? What I call that is a thing called a high pass filter. It passes high frequencies and gets rid of low frequencies. All right, that's a term. Filtering is a term you may have heard before. All right, but that's what I'm trying to do is I'm trying to go through and trying to figure out a way to do that. And I want to do it digitally. So I want to take a digital copy. I want to take a WAV file and I want to process that thing. So what I do with that is I say, well, and I tried. So when I clean it up, right, what I have in here is code that cleaned it up. All right, we're going to talk about that code. But when I play the cleaned up version of it, the noise is gone. Unfortunately, there's no way to stop it once you start it. All right. So to do that, what I can do is I can think of the problem like what I've got right here. If I had a voltage source, and you could probably do this in the lab, you could probably go up in the lab and you could actually take that WAV file and upload it to a function generator and have the function generator play it. All right, and basically, you wouldn't hear it, but it would be a voltage coming out of the function generator. And then I could build a circuit like this one. The output here would be the clean, and this would be the noisy one. All right. So in other words, this would be the top wave from the previous slide, and this would be the bottom. This particular circuit is what I would call a high pass filter. All right, that terminology is not all that particularly important to us, but that's what this thing is. All right, if I sat down and I did, first of all, I'll get a differential equation from this, and I have the differential equation there on the next slide. If I were to say, how do I write a differential equation here to figure out the relationship between V in and V out, how would I do it in this case? So that one we talked about from the homework there was a KCL. What would I do in this case? I'd do a KVL, right? I'd do a KVL in this case. If I did a KVL, what I would end up with is this, okay? I have this equation here. So and you should be able to figure out where that came from, right? Can I do that in a computer? In other words, could your microcontroller solve this thing? If I wanted to implement this in real time, so in other words, let's say I have samples that I want to process in real time, right? In a microcontroller that's sitting inside of your phone's audio processor, right? I wanted to process that in real time. Your phone is effectively doing something like this, but is it dealing with derivatives? In other words, am I solving for V out? How does your phone deal with that? Your phone has that circuit implemented digitally. In other words, there's code that does that circuit. Would it begin with this? No. Why not? Well, yeah. So first of all, if I'm talking about a circuit, I'm talking about something in the analog domain. What's the difference between analog and digital?
Analog's continuous, digital has discrete values.
And discrete and continuous in what sense? Because there's two sets of things to think about. If I'm looking at a voltage, a voltage, goes up and goes down like this. There's two dimensions to this, right? One of them is the voltage, one of them is time. So when you say continuous how?
The voltage varies continuously with time.
So in analog, both the voltage and the time are continuous. Okay. In digital, both the value and the time are discontinuous. They're both stepped. All right. But the way we tend to think of things actually is continuous time versus discrete time. Meaning, what I do is I take samples of this thing. So rather than time being continuous, time becomes stepped. Okay. So we're gonna figure out how to do that. How do we? Because there's a question there. If I decide to sample, no, the operation that I'm doing here is I'm taking a continuous waveform and I am sampling it. Right. So I'm going to use that term a lot. I'm sampling it. I'm picking values off of it. I'm going to pick values off at a regular rate. Okay. What's the hard question there to answer? If I pick values from that waveform, what do I want to make sure of?
Is it what step in time do you use?
What step in time do I use? That's exactly right. Yeah. Because if I make the steps too close together, what's the bad thing about having them too close together? Well, then I have a lot of data. All right. If I make them too far apart, what's the problem? It's not accurate, right? In other words, if I sampled at, let's say this point and this point and this point and this point, well, then that thing looked like zero, right? Because if I think about it, if I only got a sample here and a sample here and a sample here and a sample here, I wouldn't know that there was a sine wave there at all, right? So I got to be careful about how I choose those steps, okay? And I probably don't want to choose too many because then I'm going to have a lot of values in memory, right? That's, so you can kind of conceptualize what's sort of going on with that, okay? All right, so what I want to do is I want to say, all right, well, how would I do this? The way I would do this is I would go back to the definition of the derivative, all right, which I shouldn't have written out there. I should have had you guys tell me what's the definition of a derivative, right? In words, what is that equation I've got there on the screen? It's the definition of a derivative. Okay, but what is that saying? So the left is the derivative. What's on the right?
It's the slope formula where you take the limit as the change in time approaches zero.
Yeah. So the definition of a derivative, right, was that if I had a function that's not straight, I took the slope at a point, right? I took the slope at a point, and what I did was I tried to make sure that when I'm doing the slope, it's the rise over the run, right? So I tried to make the run as tiny as possible. Okay? And that way, the line that I'm drawing tangent to the function there is really representing the local change. All right, and I've come up with a way to be able to look at any function and take its derivative, at least any continuous function and take its derivative. To be perfectly honest, I shouldn't say this and then record this and put it online, but calculus is pretty useless, right? The idea of, you guys can agree with me on that, right? But the idea of taking the derivative of the log of x and knowing that that's 1 over x isn't all that particularly useful as an exercise, right? But the ability of this statement here and what this can do powerfully in a computer, that's actually a pretty useful statement, all right? Because a computer can do all the work for you, right? So at this point, a lot of the continuous time calculus result that this limit piece isn't really all that useful on a practical basis for us. What is useful is actually saying, well, what happens if I wanted to try to use this in practice to solve things numerically, okay? So what happens if I say, all right, let's choose a value of delta t, and let's just make it small, right? So the question here is, this says take the limit as delta t goes to 0. Well, let me just say delta t is going to be small, all right? Not that it's vanishingly small, but let's just say delta t is small. Okay, where we need to go back and we need to focus on what does small mean, right? Because small does have a meaning. We need to come up with a way to choose that. All right. So if I made that decision, I could say that the derivative dy by dt is something mathematicians don't like to do, but I'm going to say it's approximately this. Okay. That's approximately true as long as delta t is small. Okay. It's not perfect, but it's an approximation. Okay. So what I can do is, if I use this approach, what I do is I'm saying I'm to try to go digital, I try to discretize the whole thing. So I try to look at solving for y of 0. And then what would be the next time I could solve for with this thing? So I can solve for the value at y of 0. What would be the first time I could solve for? What would be the first t value I could solve for, probably?
0 plus delta t.
0 plus delta t, yeah. Or the next one would be 2 delta t, right? So 0 plus delta t plus delta t. Then the next one would be 3 delta t. So in other words, I can solve at specific points in time. So what I could say here effectively is, just for sake of argument, let's say delta t is 1 microsecond. So I can solve for the value of this thing at y of 0 at time t equal to 0, and then at 1 microsecond, and then at 2 microseconds, so on and so forth, right? And that's enough. Technically, that's what you've been doing in MATLAB anyway, right? Because in MATLAB, when you guys have done your solutions, or even when your calculator, your TI, whatever was graphing things for you, it was choosing a time step. So far, I've given you a time step, right? I've always told you, okay, make your time vector and make it the period divided by 1,000. I've told you a delta t that I know is going to make the function look correct. What does MATLAB do when it plots stuff anyway? So when it plots sine, right? It didn't plot that perfect sine wave, did it? In other words, this thing doesn't have infinitely many points. Like sine, t is a real number. Between 0 and 1, how many numbers are between 0 and 1? How many real numbers exist between 0 and 1? Infinite. Yeah, right? So I told you what times to plot it at, right? So that means there's actually points in those graphs anyway. What do you think MATLAB does between those points? What would you do between those points? You draw a line between them, right? If I told you I had samples at these points, you would say, okay, well, they're probably connected by straight lines, right? So what did I do? I basically chose the points small enough for you that those straight lines were so small that you didn't even see it, right? You don't notice that fluctuation. All right, so we got a lot to say about how we choose that, but first thing I want to do is to figure out how do I make this jump? What I want to do is I want to get the derivatives out of there, and I want to replace the derivatives with this expression. All right. In fact, I'm going to say if we make our delta t small enough, then I'm going to do the thing that a mathematician really wouldn't like, and say, let's make it small enough that that's effectively equal to each other. All right. That's the definition that I want to try to make. All right. So how do I approach this? Let's say I've got this circuit. All right. This circuit gives way to this equation where the y's and the x's would be voltages, right? And there would be some initial condition. So somehow I would solve for that. And I don't want to solve for the whole thing. But what I want to do is I want to take this thing and I want to turn it into something I can put into a computer, something that I could implement some code to do. Okay. So let's start with this problem. All right, let's say we've got this particular differential equation. I'm given an initial condition, and I want to quote unquote discretize it, right? The term discretizing means that I want to turn this into something that the computer can do, that it has discrete steps, okay? Rather than being continuous in time, it has discrete steps in time, okay? All right, so given all that information, how do we approach this? How should I start? What's step one, do you think? Yeah, so I need to substitute in that definition of the derivative, okay? I need to substitute that in. So when I look at this, I'm going to say, well, dy by dt, I'm going to replace that. So we said that dy by dt was approximately y of t plus delta t minus y of t all over delta t. And I'm going to say, all right, if my delta t is small enough, then I can think of this as being n equal to. Right? With delta t small. That could be a really bad choice, right? Again, we got to talk about that choice later. All right. If that's a bad choice for delta t, then this is a really bad approach. All right. So we got to think carefully about what that's going to be. So if that's the case, what I got to do is I got to substitute that into this expression over here. So I get this tau. Notice what I did. I did tau in terms of time constant. I don't want to worry about R's and C's and all that stuff. I'm just calling that's some constant tau. Okay. Tau dy dt plus y. Now, I substitute in this expression. So I have y of t plus delta t minus y of t all over delta t plus y equals x of t. Right? So I just took that equation on the left and I substituted Newton's definition of a derivative in there. Okay. Now at this point, I've taken a differential equation and I've turned it into an algebra equation. All right. When I say I turn it into an algebra equation, if I think about this, y of t plus delta t is a variable. Right? Y of t is a variable. So I can rearrange this thing and I can find a way to solve for y of t plus delta t. So let's do that. Let's say I want to solve for y of t plus delta t. So what do I do here? Well, I can say this problem turns itself into, let's see, tau times y of t plus delta t minus y of t all over delta t equals x of t minus y of t, right? Like that. And what I want to do is this is an ugly looking equation to me, right? I don't like this tau and delta t. I'm going to make a definition here and I'm going to say, I want A to be equal to tau over delta t like that, okay? So I'm going to write this thing like this. Okay. A times that whole thing is equal to that. Okay. So let's say I wanted to solve for y of t plus delta t. Like that. How can I solve that? What's my algebra that I got to do here? Divide by a and then add y of t, right? Yeah. So I'd say x of t minus y of t all divided by a plus y of t. All right, that expression is actually a pretty straightforward thing for a computer to do. All right, so let's see how we would try to go about this. Okay, so there's that expression here. All right, this is the equation from the previous slide that I've written out. All right, so I have y of t plus delta t is equal to that expression right there. And again, I said a is equal to tau over delta t. One constant is equal to the relationship between two other constants, right? That's basically what I'm sort of saying. All right, so let's see how we would use this. All right. At time t equal to 0, looking at this whole expression here. So first of all, let's go back to this. X of t, I've kept this very general, but if I gave you this problem right now, what would x of t be? X of t would be a known thing, wouldn't it? Like x of t would be a cosine function, or it would be a step or whatever. So x of t would be a known thing. And what thing do you always also have to know to be able to solve any differential equation? An initial value, okay? So at t equal to 0, all right, at t equal to 0, let me plug in t equal to 0. If I plug in t equal to 0, this expression right here becomes y of delta t equals x of 0 minus y of 0 plus a times y of 0 all over a. Is there anything on the right side that I don't know? In other words, if this came from a circuit, I would know what tau is, right? Delta t, we said we had to choose. So I know what this a value is, right? I know y of 0, right? And I know x of 0. So that's all known. In other words, I can just solve for y of delta t is. So what did I just do with this? If I think about what's going on, basically at time t equal to 0, if I think about time here, let's say here's y of t, and here's t. Let's say here's delta t right here, and here's 2 delta t, and here's 3 delta t. Let's say this thing's going along like this. At time t equals delta t, I can calculate the value of y at time t equal delta t using only the values at y equals 0. Because I knew what the slope was, right? As long as my delta t was small enough, I knew that what was happening, that differential equation thing told me that there was, if I think about it like this, right? The value at time delta t depends only on whatever x was at the previous value and whatever the slope was at the previous value. Okay? So I can kind of predict what the future value is going to be. Using that, that's really what we're doing, is we're using this definition of the derivative to predict the value in the future. I'm predicting the value at delta t, where delta t is a little bit ahead of right now. Okay, so 2 delta t, a little bit later. What happens at 2 delta t? How would I write this then? Well, I wouldn't double the whole equation. What I would do is I would plug in t equal to, so let's say, if I plug in t, what I'm saying here is that at t equal to delta t, I plug in delta t into that expression, right? So I get y of 2 delta t. And what do I do with everything here? I sub delta t into there, right? So I say x of delta t minus y of delta t plus a times y of delta t, all divided by a. And the important thing was at t equal to 0, I calculated the value at y of delta t. At t equal to 0, I calculated the value at delta t. Now what am I doing? I'm saying at 2 delta t, I'm calculating the value using the values that I already computed. Okay, so at t equal to 0, I calculated the value at delta t. At delta t, I'm calculating the value at 2 delta t. I'm predicting what it's going to be. So what am I going to do at 3 delta t? I'm going to predict the value at 3 delta t based on what? The 2 delta t value, right? So I'm going to have x of 2 delta t minus y of 2 delta t plus a times y of 2 delta t, all divided by a, right? All right, then that's it, kind of neatly written out, I guess. What I can see in general, right? If I try to generalize this here, what is that saying? That's a generalization of what I just did. What is that saying in general right there? Yeah, so it's basically saying the value at the next time step, the n plus 1th time step, is predicted by the nth time step. So if I know all the values at time n delta t, I can figure out the value at n plus 1 times delta t. So when you look at that, if I look at this expression right here, n plus 1 times delta t, n delta t, n delta t, n delta t, all that, I don't actually need to have the delta t in there, don't I? I need to know what it is, but if I think about this just as, if I think about it, I'm computing a series of numbers. I'm computing the value at delta t, 2 delta t, 3 delta t, 4 delta t, whatever. But each of those is just a number, right? In a computer, those numbers just sit in an array of some kind, right? So I don't even really need to keep the time around. I can just say the next value depends on the previous values, okay? And this is actually a more useful way for me to think about what a differential equation is actually even telling me, right? Just from a physical perspective, because it tells me that the value of the output in the future depends on the value of the output right now and the input right now, right? So I mean, actually a little bit more intuitive way to kind of think about what a differential equation is even really telling you, I think, okay? So you're always having a prediction about what's going to happen in the future based on what the input is and based on what the current value is. So what that sort of says to me, the way I like to think about this is if I think about time, I could think of this just in the context of like a spreadsheet if I set this up, right? So in this particular case, looking at the numbers I wrote out here, what's my value of delta t? What is it? 1 over tau.
0.001.
Yeah, 0.001. 0.001. Now that's somehow probably related to tau, right? But it's not necessarily 1 over tau, but I bet they're probably related, which is what we'll see, right? But delta t is 0.001. So the values I'm getting, so this is here, this is 0, this is delta t, this is 2 delta t, this is 3 delta t, so on and so forth, right? So the way I look at this is I can think of, this is the values of y of t. Somehow I sampled some function here to get this, right? I can also say that the first entry is this same value, y of delta t. The second entry is the same value. I can think of this as two different ways. I can think of this as the way it would just appear in a vector. Like if I just had an array or a vector in memory, right? You don't think of that value in memory as having a time associated with it, right? You just think of that as a value in memory, right? Or a value in an array. That's what I'm doing here. So in other words, these values are the same, but their index is different, right? When you have a continuous time function, you're indexing it by time. If I have a discrete function like this, I'm indexing it by sample. And I'm saying, well, the first sample, the second sample, the third sample, right? It becomes a little bit easier to think of it that way, right? Because the second sample is always the second sample, no matter what the delta t is. Okay, it's a more general way of kind of thinking about this, right? They're just numbers in an array. Okay, so what I want to do is, take a look at how would I code this then, right? How would I code this? All right, so what I did was I did a very step-by-step process. What am I doing? In the context of computers, I'm doing what? I'm using the values at 0 to figure out delta t. I'm using and look at it this way. I use the values at 0 to tell me the values at 0.001. And the values at 0.001 to know them at 0.002. And the values at 0.002 to figure out the value of 0.003. What am I doing? What do I call that? In the context of computing, what do I call that? What's that? Well, okay, I could be using the linked list to compute it. I'm iterating, right? This is an iterative process. It's for loop. For loop will do that. And a linked list would be a way to try to maybe implement that. But a for loop would be a good way to try it. Okay. So let's look at what I wrote here in my code. Okay. If you look at what I have in my code, I basically have taken this expression right here, and I have written it up into this for loop. So y of n plus 1 is equal to this whole thing here, right? So here's y of n plus 1. I basically just implemented this statement, this mathematical equation into this line of code, okay? And I'm looping through all the time values that I want to loop through, okay? And somehow I chose my delta t somewhere else. Okay, we're going to come back to, again, how I chose the delta t, because that is important. But this code's pretty straightforward to solve this, right? What's the if statement here? Why do I have an if statement? Yeah, so when I think about it at time t equal to 0, right? I need to say that the output, all right, I need to just throw in that the first entry is equal to 0. There's no at each time step, I'm computing the value at the next time step, right? So effectively, I got to just throw the initial condition into there, right? That's why I did that if statement. All right, so the if statement shouldn't be all that important. Most of the time, you're going into this else. Okay, so when I do that, let's take a specific example here. All right, so I took this particular circuit, right? And so in this case, I've got my tau is 0.001, not 0.0, just 0.01. Okay, and my input is 4 cosine omega t u of t. And I want to solve for what y is going to be, but I want to solve for it without having to guess and all that kind of crap. I just want to solve it. And I want to generate a graph of it. Okay, and I've got this initial condition. So I coded that up right here. All right, so let's take a look at what I did. So I was told that y of 0 was equal to 10. All right, so what I did was I just basically went through and I said, I'm going to, and let me write it again this way, x of n minus y of n plus a times y of n, all divided by a, where a is equal to tau divided by delta t. Okay, so again, I made a decision here on what delta t is. Okay, but if you follow along with what I did, I put in the initial condition, I put in tau, and then I basically wrote this equation, tau divided by delta t. Okay, then I set up a time vector, and I did something I don't necessarily have to do, but I used this command here called zeros. Zeros size t. I don't think you guys have used that yet. Maybe some of you have, but what the heck do you think that does? Makes a zero vector with the size of t. In other words, there's a vector that's the same size as the time vector, all of zeros. Okay. Don't necessarily need to do that, but I did that here. Okay. And then I created my x equals 4 cosine omega t. Now, omega was defined somewhere else. Okay. And I did that on purpose. All right. So there's my expression. And I just wrote this for loop here to create this thing. Okay. Now, this will give me a plot at the end of the day of what this thing looks like. Okay. So question then basically is, how do I make a decision on delta t? I said delta t was tau divided by 1,000. How do I make that decision? How do I choose that? How do I make that choice for my delta t? I said it was, I always say it's something divided by 1,000, right? Basically everything I gave you is something divided by 1,000, right? Where did I come up with that? Tell me how you think you would come up with that. All right, so let's go back to this. Without doing any work, what is the solution for this? Right. So in other words, you can tell me there's specific details of the math, but you should know what the general form of that solution looks like. There's two pieces, right? What are the two pieces to that solution? Transient and steady state. What's the transient solution? Or look at this way. What's the steady state solution? If I put in 4 cosine omega t, I know that the steady state solution has to be b cosine omega t plus phi. All right. In other words, I put a cosine in, I get a cosine out. Right. That's always going to be the case. Right. What does the transient look like? C e to the st. And if I solved in this case, I would have 0.01 s plus 1 equals 0. So s equals what? What's S equal to here? -1 over 0.01. So -1 over tau. Right? So I get e to the negative t over tau. So there's two things in that solution, right? There's an exponential that is decaying and going away, and there's a cosine that never goes away. Okay. So the way I kind of think about this is, it's like, to me, there's two features. All right. So if I think about this thing, I have that y of t equals c e to the negative t over tau plus b cosine omega t plus phi, like that. There's two sets of features here. All right. So this is feature number 1, and this is feature number 2. Right. There's two things happening. And if I want the answer to be accurate, if I want my graph to be accurate, what do I have to make sure of? What do I have to capture? There's two features. I got to capture all those features, right? Got to capture the transient, and I have to capture the steady state. So I got to think carefully about this. So the transient, what does the transient look like if I plotted that versus time by itself? You should know this. Yeah. Okay, it goes like this. Okay. Starts high, goes low. What about b cosine omega t? Well, he goes like this. What sets let me keep going on this guy. What sets the timing of this? How quickly does this guy become 0? But technically it takes forever, right? But there's a practical definition of forever. How long does it really take for this thing to become equal to 0? Yeah, in about 5 time constants. This thing here, this particular, or this transient solution should become equal to 0 in about 5 tau. Okay, so that gives me a sense of how long it takes to go from beginning to end, right? That tells me a good thing here. So if I look at this here, the way I would say this is, I want to choose my delta t so that it's much, much less than 5 tau. Okay. So thinking about that for a second, have you guys seen this before? This much, much less than? Right. That's a common thing in engineering, where I want to say delta t is much, much smaller than that value. Where much, much smaller than has a very technical definition of probably 100 times smaller would be a good choice, right? That's much, much smaller than. So it's 100 times bigger.
So I think it's shifting to the left or shifting to the right by
Yeah. Yeah. I mean, you're just basically shifting the decimal point a couple of spaces to the left, right? So basically, the way I think of it is delta t, if it's 100 times smaller than 5 tau, then it's 1% of 5 tau. That means in each time step, I would advance 1%. Okay, it's kind of a reasonable way to think about it. Now, that's the way to think about this transient. What about this b cosine omega t plus phi? Can I get some timing on this guy? How fast is this b cosine omega t changing? What's that? Well, it's based on the period, based on the frequency, right? So when I look at this, omega is, how does omega relate to the period? 2 pi over t. Okay. And if I want to be able to see that waveform clearly, right? What I've kind of always been saying is that if I choose a delta t, a time step that is much, much smaller than t, then I probably have enough points that it's going to look accurate. All right. Now, some people, if you're a real purist, you probably shudder at my way of thinking about this, right? So there is a theory that exists for how you sample waveforms called the Nyquist theorem. All right. We don't need to get into that because I think this is kind of intuitive a little bit, or should be intuitive. If I want to see that thing accurately, I want to make sure that the spacing between the points in it is much, much smaller than the amount of time it is in one period. So I'm going to use my same definition here. So I want to choose delta t to be, I don't know, less than t over 100. And I want delta t to be less than 5 tau over 100. I need to make sure I choose a delta t that satisfies both of those conditions. If I don't, then it's going to look weird. Okay. And this is where we need, this is what I'm asking you to do in the project ultimately is pretty straightforward if you get this concept, right? I need to choose the values of the time steps so that things look appropriate. When you use a tool like multisim to solve a circuit, that's what it's doing. One of the parameters you give to multisim is you kind of tell it, well, what time step should you choose, right? So when multisim doesn't give me the right answer, which for the circuits that you guys solve, it pretty much always does. But there's a lot of circuits that you would solve where it may have a bad choice for the delta t, and you have to kind of guide it. You have to use your brain a little bit to think about what it needs to be. Okay, so I have these two conditions here. All right. So the way I think, so this is what I basically do, or the way I think about it. If I have something like this, I always need to choose a time step that allows us to see what I call the quote unquote smallest feature. So is the smallest feature one period or is it the transient? Right. So, and if I, this would become trivial if I had a transient and a step function, right? Because the step function is pretty easy to see. Right, there's no time variation to a step function, right? It turns on and that's flat. It doesn't vary as a function of time. So the way I look at this is, again, the way that I do this is I say the transient lasts for 5 tau. So I need to choose delta t much, much less than 5 tau, or I need to choose delta t much, much less than a period. So the important thing is this last piece I'm saying right here, looking at both of these choices, delta t has to be the smaller of the two choices. If I choose the bigger of the two, then I'm going to screw one of them up. Okay. So I need to look at which one's going to be the smallest. So let's look at an example. All right. Let's go back to the problem that I started out with. All right. So I had, let's say my tau is this. My tau is 0.001. Okay. And my omega is 2 pi times 100. Okay. So looking at this here, a couple of things I want to figure out. My tau is 0.001. So how long does it take for this transient to die off? Without knowing anything about what the height of that transient is or anything like that, how long does it take for that transient to die out? So five tau, yeah. So this guy, so 5 tau in this case would be equal to 0.0005. How many seconds is that? What's the units there? It's 0.5 milliseconds or 500 microseconds. Okay, that's 5 tau. So this whole transient only lasts 5 tau. Now, what's the period of this guy over here? What's the period of that cosine? 2 pi over omega. So if I have 2 pi 100, 1 over 100, or 0.01 seconds. Okay. So what I'm saying here, if I go back to my two constraints, I said I need to be able to see the smallest of those two. So the way I looked at this is I said, all right, well, I wanted to choose delta t to be much, much less than 5 tau and make sure that delta t is much, much less than a period. Okay. And looking at the two choices, I need to make sure I choose the smaller of the two. Okay. So let's take a look here for a second. So one choice, so let's say delta t, I don't know. So choice 1, we'll call it. Choice 1 would be that my delta t could be much, much less than 5 tau or 0.0005. And what did I say was my decision for much, much less than? Divided by 100. So that would be, oh boy, I guess I wrote it down here. That's why I wrote it down here. 5, so 0.0005, 500 microseconds divided by 100 works out to be 5 microseconds. Okay. What about for this guy? My choice 2 is my delta t much less than a period, which in this case is 0.01 seconds. Okay. If I go by that 100 choice, right? T divided by 100, what's that in this case? 0.0001 divided by 100. That's 0.0001 seconds, or 100 microseconds. Okay. So in other words, to see the cosine clearly, my steps have to be at least 100 microseconds. They could be smaller, right? But I'm saying it needs to be at least 100 microseconds. To see the transient accurately, I'm saying it needs to be 5 microseconds. So which one should I choose for my delta t?
5.
5 microseconds. Okay, 5 microseconds. So let's try that out here. All right. So I'm going to go into, I got this in MATLAB. Okay. All right, so I got my tau. I'm going to divide it by 100. So I'm going to do it the 5 microseconds. My omega is that. All right, so I'm going to try to run this. That's not the right, there we go. There it is there. Now, we chose our tau here, or we chose our delta t on the basis of the transient response. Meaning the transient response is very quick. So do you even see the transient here? My initial condition was 10, remember. Do I even see it? Well, you can, yeah, you can kind of see it there. All right, you can kind of see it. So if I zoom in here on this thing, there we go. I go to the zoom. All right, I really zoom in. There it is. Right. So I made sure that I chose my time step to be able to accurately get that thing represented. Right. So here's what I get in that particular case. What happens if I had chose something stupid? Right. Let's say I chose 100. Let's say I chose 100 microseconds instead of 5 microseconds. What would it look like in that case? What do you think the graph's going to look like? If I choose my time step to be 100 microseconds instead of 5, what's it going to look like? The steady state will look normal. Will I even see the transient? Will it even be there? This thing's going to tell me. So let's take a look. So if I how long do we say it takes for the transient to die off? 5 tau. So 5 tau is 500 microseconds, right? So if I'm going to choose my delta t to be 100 microseconds, let's try that here. Okay, so I'm going to choose that. Choose my delta t to be, let's say, 5 microseconds. Not 5, 100 microseconds. Okay, I'll run this again. Now, if I look at this, it doesn't look that bad initially, but if I zoom in here, if I zoom in and look carefully at this, there's a big difference actually. This guy looks like a line. You remember what I had before? It looked much smoother, right? Which, you know, may not be that big of a deal, right? But I could get into a situation where I make a really bad decision, right? So if I look at this, all right, this is This is for delta t equal to 100 microseconds. This is with delta t equal to, so I did t divided by 1,000 there. But you can see over the same period of time, right? So in this case, I chose this over 600 microseconds. You can see what happens when I choose improperly. The one on the right is what it actually looks like. Okay. The one on the left is what happens if I make a bad decision. They look kind of similar, right? But it's, notice you can see what it's doing. It's drawing lines in between the different points that it gets. So I'm not really accurately representing that transient condition, right? Again, that may not necessarily matter a whole lot, and depending on the problem that you're doing. But let's say I was developing that circuit simulator. Well, this wouldn't really be representing what that circuit was doing, right? And that may be problematic, right? One of the couple of the examples you have in the project is going to be focused on actually how you analyze a transient for something you would do in power systems. So for that, I really would need to have a transient condition to be able to sort of make sure everything was designed properly. So let's go with a different example, right? Let's say I had this, all right? Let's say I have tau equal to 10, and I have omega equal to 2 pi 10,000. Okay. What would I do here? So 5 tau is how long it takes this guy to die off. So what's 5 tau in this case? 50 seconds. So my delta t should be much, much less than 50 seconds. Or my delta t should be, if I choose that very caveman way of doing it, it's going to be 50 divided by 100, which is what? 0.5 seconds. All right, what about this one here? What's my period for this guy? What's one period here? 1 over 10,000, which is 10 to the minus 4 seconds. Right? So if I want my delta t to be much, much less than a period, then I want my delta t to be at least t divided by 100, which is 10 to the minus 4 divided by 10 squared is 10 to the minus 6. So which one do I choose in this case? So this is choice 1. Right? This is choice 2. Which one do I choose? 2, right? This guy is the one I choose. If I choose that improperly, here's me choosing it improperly. Here's me choosing it on the basis of my tau. If I choose it on the basis of my tau, I just get the transient response. I don't even see that sine wave. If I choose it on the basis now of the sine wave, right, I get this. I can actually see that there's a sine wave running around on top of this whole thing. All right, so it's a really important decision that I need to make in terms of how to do this. Now we're going to look at more examples because this is the kind of stuff that you have in the project. So we're going to talk about this a lot. You should start looking at the project. The first problem on the project jumps right into doing these numeric solutions. All right, so you got a homework due today. Finish that, but don't wait till forever to start the project. All right, I've said that like 10 times already today, and I'll say it 10 times on Monday. All right, you need to get started before a couple of days before it's due. All right. All right. I am going to stop a little bit early today